Today we're going to be looking at chapter 14, meaning that 14.1 and 2 is the plan. So 14.1 talks about, begins talking about the idea of a function whose output is a vector instead of a number. We call vector valued functions. And I think that this is a good time for us to sort of contextualize the kinds of functions you're going to see in Calc 3. This is just one of the multitude of different sorts of functions that can arise when you've got more than a single variable. So you're used to seeing functions that look, in black box diagram terms, look like this. We call the function f, x is its input, and then f of x is its output. That's called the Euler notation for the function, where you write the f and the x in parentheses. You can take a group of functions like this, actually just three of them, and sort of imagine them as sort of, they're the ingredients to building a bigger black box. So you have a big black box, and inside of it there's a set of these little functions. Do I have room for three of them? There's usually three. Okay, and so for reasons that'll be clear soon, I'm going to use t as the input parameter. And the first thing that happens is you branch off, think of the wire, that it being a wire, and you just branch it off and make connections to each of these functions. I probably should have called them something. How about f, g, and h? Okay. And then the big point of this is that this overall black box diagram is now going to have three outputs coming out of it. And those are f of t, g of t, and h of t. What we want to do is consider those three to be a single thing. That's really the idea. So I wish I had a way to cover this neatly. I have to use my notes here, I suppose. The idea is that you think of this as just being a single box that has t come out and three outputs come out of it. Well, when you have such a thing, there's a shorthand for it, which is to say, look, treat these three things as the components of a vector. So call this v of t. And if you do that, then you think of it as, well, as looking more or less like this. One in, one out, except the in is a scalar and the out is a vector. I like to think of it as a cable with three different wires bundled together. But that's the vector version of it. So if you do all that, you get something that looks like this. T goes in, there's the function, I don't know what to call it now, and the output is a vector, which is a function of t. And if you really want to get access to those interior parts there, you can say that vector is f of t, g of t, h of t. So this is a vector valued function of a single real variable, and these are the component functions. That's, by the way, the term for these guys. Since they are the components of the output vector, you just call them component functions. So that's the idea with vector valued functions, but I don't have quite enough room for the s there. But I want to point out that you can think about lots of other possible options for black box diagrams, input-output pictures for a function. What if, for instance, we had a vector going in and a scalar coming out? Suppose it had some vector x as the input going into some function, and the output is a scalar, or call it, I don't know, s for scalar. The way this looks, if you kind of unwrap the wires that are in that bundle for x, it really looks like this. A three input Well, that's assuming X is a three-dimensional vector. Three inputs going into a black box and a single output coming out of it. So what we're going to look at today is single inputs, multiple outputs, but we could have had multiple inputs and single outputs. And there's a third option. You could have a vector's worth of inputs and a vector's worth of outputs. That's sort of as bad as it can get. And we will actually eventually get to looking at functions like that too, where there's, you know, in fact, they don't have to be the same number. I've shown 3 in and 3 out, but it could be 2 in and 3 out, or 3 in and 2 out. Really, you can mix and match as you want, however many inputs, however many outputs. We can do calculus in those settings. So when we do look at vector valued functions, and this is why I said I prefer to use t as the input, you can think of them as a position vector that's a function of time. And that's known as a space curve. A tremendous number of things are space curves. You know, if I'm trying to draw something on the plane, well, that would be in the plane, so maybe I should call it a plane curve, but the plane is in space, so it's still a space curve. That's cool. The way you actually draw something involves time, doesn't it? You notice how I moved along the curve as I was going? So here was where I was at t equals 0, and here I was at t equals maybe 2 seconds. That is, at every time value, there was a location in the plane. And I can't really draw in space, but you can imagine it. I have a little, you know, probably you could do something with augmented reality where I could leave a little glowing trace behind as I traced something in space. My position is a function of how long I've been drawing, or what the time is as I do something like that. So those are kind of nice. It might take you a second, it might be worth taking a second to think about what the other kind of function is that takes a vector on the input side and gives you a number out. That's saying any position in space could be an input, and we need to get a number out for each of those positions in space. There's a lot of things that work like that. For instance, in this room I'm standing in, there's a temperature gradient. I'm sure it's warmer near the ceiling than it is down near the floor, just because that's the way things work. You know, hot air rises. And that means at every location in space, we could imagine hanging a little thermometer and we'd get a number, a single number for the temperature. You can do things like that for, well, I could think about that for the temperature inside the Earth. And, you know, we really can't get thermometers there. It'd be really a problem because the thermometers would melt. But you still know that there is a single number at every point in the interior of the Earth that it represents the temperature. So that's a vector as the input, where we nail down what point we're talking about inside the Earth, and a single number is the output, whatever the temperature is. Yeah, here we're talking about there's a single number as the input, and it tells us where we are at that time. So that's the idea of a space curve. These kind of things are called parameterized. I have noticed that people from Britain pronounce this parametrized, skipping that E, but I think they still spell it that way, so I don't know. But yeah, once you've got a parameterization in mind, you should notice something about the space curve. It's not the same to draw the curve the way I did as it is to draw it in reverse, right? If I started here and went backwards along there. Now, later on, we're going to make this more formal, but for right now, just think about at each point along the curve as I was drawing it, there was a little arrow that said which way we were going. That's an orientation. When you have a thing like that, you're creating an orientation. That is, the flow of time actually provides us with this orientation. It's probably possible to come up with a parameterization that goes the reverse, in which case the little arrows would go the other way. That kind of thing right there, a little arrow that tells you which way you're moving, that actually points in the direction of motion along the curve, is known as a tangent vector. Because it is a vector, isn't it? And you see that it's tangent to the curve? So that calculus has a lot to do with things like that. All right, we're gonna move over to my screencast setup so I can show you some examples of actual curves in three-dimensional space. So I've got a Sage worksheet open here on my desktop. I just want to run you through the setup here because I've done a few things that are non-standard just to try to get slightly prettier looking graphs. The first couple of things here, setting t equal to a var and xyz equal to variables. That's not non-standard. But the next thing I've done right there is what I've done is define a function, and it takes a range for the x, a range for the y, and a range for the z variables. That's why I called the inputs here rx, ry, and rz. And what it is going to do is create a thing that looks like a jack. If you remember playing that with a jack, it's basically little sticks in the x, the y, and the z directions. And on those sticks, it also draws some arrows. There's an arrow along the x-axis that's red, an arrow along the y-axis that's green, and an arrow along the z-axis that's blue. And then this function just returns this is actually 6 different plots that is created, and what it returns is the sum of those plots. When you add plots, it just means put all the pieces together into a single plot. So the reason I went to all that is twofold. One is I like the XYZ axes to appear in my pictures so that I can sort of understand which way things are changing, what variables are changing as I look at a function. And the way Sage by default puts the axes on is by drawing a box around the whole thing and labels. One side has got X, one side has got. It's a little bit harder to follow, at least for me. So personal preference, I've put on the regular axes. The other thing the other reason for doing this is the Sage plots in 3D don't seem to be able to tell you a kind of a window to use. The graph just fills whatever volume of space it fills, and so it draws all of that. I sometimes want to see the graph, with the margins around it, so to speak. It's got some space in each of the directions around it. Other times not, but sometimes you want to do that. And so to be able to specify what would be called a viewport if we were in 2D, but a viewing tank if we're in 3D, isn't possible. At least I haven't figured out how to do it. So this kind of is a workaround for that by making this thing have a particular size. This setup for the axes, the plot will automatically fit to that, and then hopefully the thing I'm actually interested in looking at is inside that volume. So here's the first example. It just says a circle floating above the XY plane. And that's what it is, isn't it? Now, if you do these kind of plots in Sage, what's nice, I've set it up so it's spinning, but you can grab it and move it and look it around from different angles and stuff. It's cool, right? I keep disappearing when I go to do things on the thing. Well, I'm going to have to do another thing on this thing. I want to show you the source code for how to get that plot. So what I did first is define a position vector. In Sage, you don't necessarily know it's a vector, but when you see what it was set equal to, okay, that's a vector. It's got 3 components. The cosine and the sine are in the x and y slots, and the value 1 is in the z slot. Do you see how that'll make it draw the unit circle in the xy plane, but it'll do it 1 unit up in the air in the z direction. So this is the command, parametric plot 3D, that you would use in this kind of scenario, where you've got a function, or r here is really a function of a variable t, and I'm letting t run from 0 to 2 pi. thickness equals 4 is just so it shows up nicely on the screen. But if you're live looking at a plot like this, thickness equals 1 will be just fine, probably. No, so then I also created used this function that I defined above to create a little coordinate system with the vectors in it. You can see in the image there, the red vector is the x-axis. Let me put it around so it's at the front. The y vector is green, and it's the one that's going away from us, and the blue vector is z. I'm fighting it, trying to make it not rotate, but that's where it should be, in the kind of usual way of drawing the XYZ system. All right, where you actually get the plot to appear is with this final command, which is to show the plot. If you have a plotting command and you don't set it equal to something, it'll just show it. But if you set it equal to a variable, nothing happens, which it feels confusing because it's waiting for you to display the thing that you've just stuck in a variable. You do that with this command, show. I'm taking the plot, which is the circle, and that view output, which is the axes, and adding them together, making a compounding of both elements. And then frame equals false. It has to do with what I mentioned before, that CoCalc's default way of drawing things is to put a box around it showing the stuff. Oh, sorry. I must have lost connection while I was preparing to screencast. So yeah, I did. So it's now thinking that's all new, and I don't have the variable t defined. So we'll rerun that, then rerun this, and it should plot the thing. The change I made was to remove the frame equals false that was in this command before, and that's how it looks when you have a standard CoCalc thing. It draws this box around everything, and you can see that, like, there's the z-axis. It's going from -1.5 to 2. Here's x equals 0. X is running from -2 to 2, as is y. But I don't particularly like that box around everything, so I usually eliminate it. If you like it, then you can put those back in to your plots. Let's see another 3D plot, and this one is more truly three-dimensional. It's a helix, or it looks like a spring, right? How do you get that kind of thing to come out as a vector function, a vector valued function? Well, you can probably imagine the x and the y coordinates are just cosine t and sine t to make it draw a circle, because if we move this thing and look down on it, yeah, it's just tracing a circle around in the xy plane. But we also need to be changing the height. And in fact, the height is just changing in a uniform fashion as we trace along it. You got to imagine it's walking around this curve like a set of spiral staircase or something. It eventually come to the top. Well, your height is changing with time. In fact, the way I believe I did the equation for this, I just made the height be t. What did I just do? Oh, there's the. Oh, I'm sorry. I collapsed the graph rather than showing the math that made it happen, or the programming that made it happen. So, as promised, here's the r function. It's a vector. Cos t is the x coordinate, sine t is the y. Oh, see, I used t over 10. I think it just didn't look nice if I had plain t in there. The spiral was too steep. And then we do a parametric plot with r. I use the range from -20 to 20 on that, but you can do whatever. Frame equals false, removes the box. This is a nice argument to know about for these kinds of plotting things. By default, it uses 75 positions along the whatever curve you show it. And since if you put just 75 points along that and connect them with straight lines, it looks kind of jaggedy. Here, I'll let you see what it looks like if plot points is the default value of 75. See how the curve has now got sudden changes of direction on it. It looks like it does look like it's made out of straight lines. Well, just bumping that number up to something much larger makes it look smooth, even though it's always going to be just drawn by concatenating a bunch of straight lines. But if the straight lines are small enough, you don't see the change in direction, so it looks pretty good. All right, let's push on. What's the next curve I did? Another kind of spiral. This is a fun shape actually. Spiral. It's actually staying in a plane. It's it's staying in the plane z equals to 1. If I get it so that we're just seeing it edge on, you agree? Yeah, it's all happening in the plane z equals 1. And the spiraling happens by spiraling outward. I one time took apart a cuckoo clock that my parents had bought in Bavaria, and there was an object that looked just like this in it with a striker that would bang it. And it's really cool that that particular shape, made out of fairly stiff steel wire, when you bang it, it sounds like a big, deep gong. It would be like, so that this tiny little cuckoo clock could make this really impressive uh, gonging sound by having this shape as the. I don't know what it is about that particular shape. Maybe just that it's a way to compactify, put a fairly long length of wire into a small amount of space. But anyway, it sounds cool if you make one of those out of wire and ding it, you get a pretty neat sound. I guess I should show you the formula for it. I think I just did it again. Yeah, it's this one. No, it's okay. I've got it up. So what have we done? I used basically it's t times cos t and t times sine t. But I scaled it by dividing that t by 5 because if I just had a t in there, the spiral is fairly large. It moves out to fairly large sizes rather quickly. By putting t over 5, I get to see more of the legs or arcs of the spiral. And on this plot, which is, that's a lot of curvature on that whole thing as you go around the circular area, what, 4 times, 5 times? So it really needed a lot of plot points to not look like it was made out of straight line segments. It's kind of a pretty curve anyway. I don't want, I've done 2 graphs now that are actually flat, that are not true space curves. So here's another one that is actually, in 3D. You have to, there's no plane that contains this whole curve. I'm going to stop the graph when we get to the point where the y-axis is pointing away from us. Almost. What does that graph look like? What I'm seeing right now is the XZ plane flat on. The red arrow is the positive x-axis, the blue arrow is the positive z-axis. And I hope you see that looks like y equals x cubed. Of course, it would be z equals x cubed here, but yeah. If I look at the xy plane, well, wait, let's bring x back and try to get y right towards us. It doesn't quite look right because of a perspective issue, but if you didn't have some of that, I try to hold it still. If some of that purple graph wasn't there, if you were only looking at the part near the origin, what would it look like? Yeah, I think it's a parabola. So this is literally y equals x squared. This one, z equals x cubed. This one, y equals x squared. And do you see how it's got a twist to it? I hope it looks as if what you did was take a parabola and then bend one leg upward and the other leg downward, making it so that those upward and downward facing things follow along the curvature of x cubed, y equals x cubed. There is a third projection axis, which is kind of strange looking because, well, it's not a function, is it? The problem is that none of this stuff has to be a function in terms of, z is a function of x, or y is a function of x, or any of the other variables is a function of the other. Everything is a function when you think of them as being functions of t, however. So the fact that this looks like it fails the vertical line test shouldn't scare you. because those vertical points, those points that might be directly above one another in this plot, so they do have the same x coordinate, or is it y? They do have the same y coordinate, but they occur at different times. So as far as time being the input variable, the domain, there's no problem of failing of, I guess we would call it the vertical line test. The time equals, well, no other way to refer to it really properly, because we're talking about 4 dimensions. Right? The time is one axis, x, y, and z are the other 3 in 4 dimensions. I don't know how to make sense of saying vertical line test, but it's still a function. Distinct t values give you distinct, I think I just said that wrong. At the same t value, you never have 2 distinct x, y, z values, 2 distinct vectors. But there actually is a graph that looks just like that, which is the graph of y squared equals x cubed, not a easy, oh heck, let's do a Desmos real quick and we'll see it. Where's Desmos? There it is. I'm sorry, is it y squared equals x cubed or the other way? Oh, let's just see. Yeah, I guessed right. So y squared equals x cubed is the thing we were just seeing. Not a function, but it is a relation, and Desmos is fine with graphing relations, so that's fine. Anyway, this particular curve, now that I've shown you what the pieces of it look like, the projections of it look like, maybe it will be clear why the formula has to be what it is. The x coordinate is just the same as the t coordinate. That is, x is equal to t, and then t squared is y, which means that x squared is y, and t cubed is z, so x cubed is z, because x and t are the same. So that's why we get the various projections we got there. Okay, lastly, oh no, not lastly, there's 2 last things I want to show you. This graph is called a trefoil knot. If I show it to you from above, you might see why they call it that. It actually is the way you make a overhand knot, except knots in the math world have a slightly funny behavior. They're different from knots that are actually made in rope, because usually if you make a knot in a rope, there's an end to the rope and another end of the rope, and you make the knot, and then you still have ends. But in mathematics, what they do is just glue those ends together to make a knot. So the mathematical definition of a knot is it's an embedding of a circle somehow into 3 dimensions in such a way that it can't be continuously morphed into just a circle again. The trefoil knot is an example of that, probably one of the simplest examples of it. I'm trying to let you see where the knot passes over and under itself by moving it around in space. That one crosses over that one, then under this one, then over there. In fact, it's what's known as an alternating knot, because as you look at as you trace your way around it, it's always over, then under, then over, then under. The way this actually got drawn is sort of intriguing. So let me get to the source code for it, and I'll make a little change. First of all, here's the functions that make up it. They're not easy. I have 3 times cos t plus cos t times cos of alpha times t. I made alpha be 1.5, 3 halves. I knew in advance that I was going to need to fiddle around with this until I found the right alpha to make that knot. So it turned out that alpha was 3 halves was the right thing. But, you'll see the y coordinate is kind of similar to the x coordinate, but it's instead of starting with 3 cos t, it starts with 3 sine t. And then it's the sine of t times the cos of alpha times t. And finally, the z coordinate is just the sine of alpha t. So why such funny looking things? Well, those particular functions force the curve that we just drew to lie on the surface which I have created here, but I didn't add to the plot right away. So what I made here is a function of two variables, u and v. And I called it torus because, in fact, that's what it's equal to. It gives a donut. A torus is just a fancy way to talk about a donut. So Q here is a parametric plot of that function of two variables. Well, let's see what it looks like. Well, we won't see what unless I add it in here. Okay, go. All right. So it's pretty cool looking when you see it this way. The blue graph stays on the surface of the red donut. I tried to make the donut a little bit see-through so you can still see the blue graph down inside of it. Anyway, that one was just for fun because I wanted you to see something that, well, that leads to some pretty interesting stuff. That's a whole beautiful area of math called low-dimensional topology. Finally, I want to show you an example from the textbook. This is example 5, and we have a question about it. The formula for this thing, whoops, I always do the wrong, there it is. The formula for this thing is, I've just got a 1.5 on sine and cosine functions to make it have a radius of 1.5. Cosine of pi times t means that as t goes from 0 to 1, we'll do a full half of a revolution. So that makes it easier to think about what range you might want on the t variable. And then the z-coordinate here, look at that thing, the exponential function of negative something times t. Well, a negative exponential, e to the minus t, you should know is something that approaches 0 as t goes off to infinity. It's it's like e to the x except flipped around across the y-axis. You get a, yeah, we've got Desmos here. Let's look at that one while we're at it. Y equals e to the negative x. Yeah. So starting out at 0, you're at a value of 1, but it quickly decays down towards 0. That's the kind of thing I'm looking to show here. All right, so we're going around a circle, but our height is dropping down towards 0. That's why you should read that. When you look at the slightly modified cosine and sine functions, one modification makes the radius a little bigger, the other is just to make it, it's a different parameterization of the circle so that we go around the circle in 2 seconds rather than in 6.28 seconds. Anyway, when we parametrically plot that, we get this lovely picture. And it's kind of neat looking. Actually, I've seen real springs that have this effect on them. As you get near the end, they sort of tighten up the spirals until you get a very close together spirals at the very bottom. In fact, the last thing is just a loop. So this is an interesting looking thing, but it actually has some interesting properties when you think about limits, which is what we're going to go do next on the chalkboard, or the whiteboard. Well, now that we've seen some examples of space curves, let's try to get started on doing calculus with them. You probably think back a couple of semesters and remember how the beginning of Calc 1 went. You had to deal first with limits because what we really care about is derivatives and integrals, but those things are defined in terms of limits. So first, we're going to very briefly talk about limits of vector valued functions. Now, the reason this can be a very brief discussion is because you already know how the limits of regular functions work. And the way the limits of vector valued functions work, well, they just are sort of the conglomeration of a bunch of regular function limits. So let's give an example of this, I suppose. Suppose I call it r of t, and that's a vector. And it has coordinate functions. I'm going to name these functions after the coordinates. So we'll call it x of t, y of t, and z of t. I think that may look funny to people at first because, you know, x, y, and z are supposed to be the variables that gives us the axes, but you can just reuse the as a name of a function. It's kind of nice that x of t literally is the output the x value when you plug in a t. Anyway, what should we do with the limit as t goes to some value a of r of t? Well, I'll tell you, that r needs a hat on it. It's almost the only thing you could think about doing. What you want to do is figure out what happens to those coordinate functions as t goes to a. And what that looks like is that the limit here kind of can distribute into the vector. Let me write this in two stages. First, we'll take the limit, one more hump on that m, as t goes to a, and replacing r of t with this expression in terms of its coordinate functions. And then we'll distribute the limit-taking process into the pieces of the vector. So it finally looks like so. Whoops, not like that. Start with the vector brace. Inside in the x-coordinate, we'll have the limit as t goes to a of x of t. And then in the y-coordinate, it'll be the limit as t goes to a, of y of t. And finally, the limit t going to a again of z of t. Now you may recall a big deal back in when we were doing limits in Calc 1 was, does the limit exist? And what's going to be the deal with this? This limit exists precisely when these limits exist. They have to all three exist, and then this one is valid. That's kind of the whole deal. You sort of pass the work from up down the line, basically. You've got a question about the limit of a vector, just turn it into a question about the limits of the components of that vector. Another concept that's of the same sort, we just sort of pass the problem down to the components, is the question of whether a vector valued function represents a continuous curve. Now, everything you ever see in real life operates continuously. But at the quantum level, the universe does not work in a continuous fashion. A particle can disappear in one location and then reappear instantaneously in another location. There's an effect called quantum tunneling, where actually a current is created in some semiconductor devices that depends on this effect, that electrons can just poof out of existence on one place and reappear in another place. If you think about it at the macroscopic scale, though, it's really quite bizarre. Can you imagine throwing an object and watching it in flight, and then suddenly, bam, it's not there, and it's coming down here and doing something else? It would be crazy. But that's what discontinuity looks like. You have some object following along a path, and then poof, it's out of existence there, and it comes down and reappears over here and continues on with its thing. Imagine what you would think if you saw like a bug doing this, right? And then it reappears there and keeps moving. That would be very shocking. This is what happens in science fiction shows. There's a thing in Star Trek where they call it the transporter. Basically, you turn a person into pure energy and then reassemble that person elsewhere, and the life of that person is the track that person has followed becomes discontinuous. So when is a function, this jump right in here is known as a discontinuity. And we usually kind of think more about the other side of the coin. When is a function continuous? So a function is continuous at a particular value if the limits, one from the left and one from the right, at that agree with the actual function value. So let me say it this way. The limit as t goes to a of vector valued function r of t, vector r of t, has to be the same as the limit as t goes to a from below. By the way, let's look at them as above and below rather than just the limit. Actually, the limit is when you don't have either a plus or a minus, and it means that these two things agree. But the limit is t goes to a from values that are bigger than a, whereas t goes to a through values that are smaller than a. That's what those things mean. But to be continuous means that both of these limits agree, and furthermore, you can get that value by just plugging a into the vector function. So the limit from above equals the limit from below, and it's the same thing as the function. There is a possibility where that third thing doesn't happen. You could have the limit from the one side go to a particular location, the limit from the other side go to that location, but when you get to the particular t value a, you're over here. It seems like a worthless use of the transporter device. You're tracking along to here, you transport away for a millisecond, and then you come right back where you were. That's strange, but that's a discontinuity nevertheless. So we need all three things: limit from above, limit from below, and the actual value of the function at a to agree. So if you have those three elements, and this one can be just turned into just saying that the limit as t goes to a of r of t exists. But that one and this one together, that's all you need to have continuity. You know, I've sort of sketched at it. Maybe I should write this in a formalized way. Yeah. So you want to make a statement about a vector valued function r of t. It's going to be continuous at t equals to a, provided two things. The first thing is the limit as you approach a has to exist. I just noticed I left off the vector hat. Limit as t goes to a of r of t exists. And the second thing is that that limit equals to r of a. Well, I guess I should write it the way I just said. Limit t goes to a, r of t equals r just evaluated at a. So if both of those things happen, then you know you've got a continuous curve, and I'll be blunt, almost all the time this happens. We're going to see some ways in which limit of functions that are vector valued functions can not exist, even though the curve seems to be completely smooth and doing nice things. In fact, you just looked at one. That example 5 thing in the book was one of such things. So while we're here, let's do that. Yeah, I think that'll be the last bit in section 14.1 that we need to look at. So do you remember how the graph in example 5 looked? The graph of it was, it's sort of a spiral, but it's getting, the loops of the spiral are getting closer together, and then eventually kind of going around and around, approaching a circle in the plane. That's the way it looks. And so the position vector here was, let's see, we had the cosine of, I believe we used pi t in the book, but you know, it could just be cos of t, that'd be fine. The sine, again, keep the thing scaled the same way, so sine of pi t as well. But the z coordinate is e raised to the negative t. So what does that do for us? These bits make us trace around a circle, and this bit lets our height slowly get smaller and smaller and smaller. In fact, I'm sure you know as t goes towards plus infinity, this becomes e to a giant negative number. And, well, e to a giant negative number is a tiny number. So what we're talking about evaluating is this limit. Limit as t goes to, I don't know why I tried to make a double arrow there. T goes to infinity of that function, of that vector valued function. So what do you make of it? Well, the z coordinate is just doing just fine. It's going to 0. But what's happening to the x and the y coordinates? Because remember, the limit is actually defined by saying, well, it's the limit of a vector, just take the limit of the various components. That is, make a vector out of the limits. I just feel like every single time I write the word lim, it gets slightly sloppier. Actually, I'm running out of space, but it's okay because we know what the limit of e to the minus t as t goes to infinity is. That's 0. The question, though, is about these other things. Is there a limiting value to the sine of pi of t? Pi times t, or just think sine of t? No, the sine curve keeps going up and down, you know, it follows it's a sine curve, it's a wave. So this never approaches any particular value. It constantly goes as low as -1 and as high as +1, back and forth between those values. No limit there. No limit here. These guys, the way I usually write this is to say dne. I'm having a really hard time with the correct number of humps on my letters today. dne does not exist. So because one of the vector, it only took one, it turns out there's 2 of them, but anyway, one of the components doesn't have a limit. That means this thing doesn't have a limit. And yet, there is something that provides a limit. Don't you think that in a real sense, the graph is approaching that circle? I could think about the limit being the circle that's actually in the z = 0 plane. And that is actually kind of beyond where we want to go today, but that's something that people look at in like topology or real analysis. And later on math courses, you can talk about, rather than a particular position, a particular value of the vector valued function as a limit, you can have what's known as a limit set. And that circle is a limiting set for this function, but it's not just plain old limit. So for now, we would just say this guy here also does not exist because not all of its components exist.